So is my whiteboard is visible to everyone?
Yes.
Yes, sir.
Yes, sir.
Yes.
So let me just copy the question. Okay, so what is been given in this particular problem is a 100 mm pipe will carry a steam of one at 160 degrees Celsius. So 100 mm pipe means what? So diameter of the pipe is 100 mm. Okay, is it clear to everyone? So there is a 100 mm. Maybe I'll just draw. Okay, so this radius is given. This radius is given 0.05 meter. Do you all agree? 100 mm diameter is there, so radius will be 50 mm and 50 mm is converted into meter is 0.05 m. Isn't it? Yes or no?
Yes, sir.
Then again what is been given is it is planned to lag it with 100 mm preformed insulation. So there is a insulation above this particular pipe, and this insulation, with this insulation, maybe I will just draw one more circle here. Okay, and okay, so now this is the 100 mm preformed insulation is there. So this part is 0.1 m. Okay. All right. Is it clear to everyone? Hello. So this is the insulation which we have put outside this pipe. Now this particular pipe is carrying what? It is carrying a steam. It is carrying a steam. Just a minute. Outside air film. Okay, let me read out completely. The outside air film coefficient of the lagged pipe is estimated. Okay, so H naught here is given as 5 watt per meter square degree Celsius, and that from the bare pipe is at 160. Okay, so here Ti, and that from the bare pipe at the 160 degree Celsius would be 20 watt per meter. Okay, so here this temperature here is given as 160 degree Celsius, and Hi is given as Hi. Just a minute. Okay, so somewhere here, if we are having a bare pipe, for a bare pipe, the temperature is given as 160 degrees Celsius, and H naught bare is given as 20 watt per meter square degree Celsius. Okay. All right. So this H naught B is the bare pipe outside here, okay. But when we are having this entire insulation, then the pipe is not exposed to the air, but instead of that, this insulation is exposed to air. In that case, H naught is 5. But when bare pipe is used, then H naught B is 20 watt per meter square degree Celsius. But in that case, temperature is also 160. Okay, so this surface temperature is 160 degrees Celsius. That is what is given. Again, thermal conductivity of the insulation is given as 0.9 plus 3 into 10 raised to power minus 4 watt per meter degree Celsius, where T in degree Celsius. So this is what is given. Okay, ambient temperature is given. Ambient temperature outside here TA is given as 30 degrees Celsius. Now what is happening is the steam is flowing through this this inside pipe, isn't it? And what is happening here is, because of heat loss, what will happen? This steam is going to get condensed, isn't it? This steam is going to get condensed, and if the steam is going to get condensed, that is, if 1 ton is going to get condensed, then it is going to cost the money which is equals to 750 per ton. Okay, so cost of the steam is given. Cost of steam is given. Cost of the steam is given, and this steam is a saturated steam. Okay, so cost of the steam is given as 750 rupees per ton. Per ton is given. Okay. Latent heat of the steam lambda S is given as 1825 kilojoule per kg, and interest rate is given in the problem. Interest rate is given as 0.18 per year. Now the question here is, if the insulation cost, if the insulation cost is 15000 RS 15000, that is 15,000 per meter cube, what is the payback period? What is the payback period? So is it clear to everyone what we are trying to say? Hello, is the problem clear?
Sir, why are we taking that steam will condense? Because we do not know whether the temperature would be below 100 degrees Celsius.
So it depends on the pressure. That's why we said that it's a saturated steam, isn't it? Yes or no?
No, sir, I did not understand.
So do you think that the steam is going to condense every time at 100 degrees Celsius?
No, sir. Yes, sir. It depends on the atmospheric pressure. I mean the.
So it depends on what pressure is there inside. That's why I am saying that the steam is a saturated steam. So that means it is going to condense at the same temperature. T equals to whatever is the inside temperature is there. Okay. Is it clear?
Yes, sir.
That's why this word is very important. It's a saturated steam. Is it clear now the problem?
Yes, sir.
So what we are saying is this pipe is carrying a saturated steam, and we don't want it to have the heat dissipation to the outside. So that's why this entire pipe we have lagged by a insulator, isn't it? Now what we wanted to find out is whatever the saving we are going to have by adding this insulation, isn't it? With that saving, how much time we need to have in order to pay back the cost of insulation. Remember, if we are putting the insulation, we are incurring some cost, but at the same time saving in the heat loss is also going to save some money, isn't it? So whether that saving in the heat dissipation outside, how much time it is going to take to compensate whatever is the amount which you have incurred for putting the insulation. That's what the question is. Is it clear? The problem is clear to everyone?
Yes, sir.
Okay. So now in this case, let's look at thermal conductivity first. Okay. So now here the temperature is here at the surface temperature here is 160 and here the outside temperature is TA is 30 degrees Celsius. Let's say if we remove this this insulation, then also the temperature is going to vary between what? It is going to vary. Maximum temperature is going to vary in this insulation is what? 160 to 30. Do you agree? So temperature variation in the insulation will be between 160 to 30 because this bare pipe has the temperature of 160. But outside temperature of this insulation is that would be slightly higher, but in a worst case scenario we can say that temperature is, let's say, 30 degrees Celsius ambient temperature. So maximum temperature variation between this bare pipe and this insulation surface here will be 160 to 30. Do you all agree? In a worst case, I am just looking at the rough estimate. Does that make sense?
Yes, sir.
So maximum variation. So I am writing this. Maximum variation in insulation temperature will be between 160 degrees Celsius to 30 degrees Celsius. Isn't it? I can write this easily. Yes or no? So now with this, let's calculate the value of thermal conductivity. So at 160 degrees Celsius, K will be given by 0.9 plus 3 into 10 raised to power minus 4 into 160. So this comes around 0.948 watt per meter degree Celsius. Similarly, at 30 degrees Celsius, K will be given by 0.9 plus 3 into 10 raised to power minus 4 into 30. So this comes around 0.909 watt per meter degree Celsius. Do you all agree with this? Remember, the thermal conductivity in this case is given as it is a variable. It is varying with temperature, isn't it? Do you all agree? Whatever I have written. Yes or no?
Yes, sir.
So now in this case, since the thermal even though if my temperature is changing from 30 degree to 160 degree, my thermal conductivity is not changing too much, isn't it? At 30 degrees Celsius it was 0.909 and at 160 it is 0.948. Is there any significant variation in thermal conductivity?
No, sir.
Is there any significant variation?
No,
it
sir.
is varying only in the second digit, isn't it? Correct?
Yes, sir.
So that means we can take that, we can use the average value of the thermal conductivity here in this problem, isn't it? We can solve this entire problem with the variable thermal conductivity as well, but then your problem is going to become too much complex, isn't it? Correct. But since my thermal conductivity is not varying too much, I can take the average value of thermal conductivity and I can go ahead with solving, isn't it? Do you all agree?
Yes, sir.
So if I take the average of this, what we get is around 0.929, almost 0.93 watt per meter degree Celsius. That is what you are going to get. Okay, so we will solve this entire problem with the assumption that thermal conductivity is constant and that constant is equals to the 0.93. With that assumption we will solve. Why we are making that assumption? Because my thermal conductivity is not varying too much with the temperature. Even if I look at the temperature variation and its effect on thermal conductivity, hardly it is going to change my answer, isn't it? Because it's not varying too much. Does it make sense?
Yes, sir.
Okay. Now in this case, see, inside heat transfer coefficient, since steam is flowing with a high velocity, clearly inside heat transfer coefficient HI will be very high. HI will be very high, isn't it? So we can calculate the overall heat transfer coefficient. So what will be the overall heat transfer coefficient with respect to the outside surface area? 1 by U naught will be 1 by H naught plus this is what you are going to get, isn't it? This is what the expression for the overall heat transfer coefficient. You also get one more factor here. That another factor is going to be what? The another factor will be R naught by Ri into 1 by Hi, isn't it? But since we are assuming that Hi is very high, that factor goes away. Remember, this is one of the simplified case we have looked at earlier. Correct. So in this case also we can find out the overall heat transfer coefficient. Now what this H naught is? This H naught is the heat transfer coefficient when we are having the insulation, isn't it? Whenever we are having the insulated pipe, this is for insulated pipe, correct. And what will be the equation for the bare pipe? Can anybody say? What will be the expression for a bare pipe? For a bare pipe, we don't need to find out the overall heat transfer coefficient because the conduction through the metal wall we have neglected. The heat transfer coefficient of the inside pipe is very high, so that part is also neglected. So that means only H naught B, isn't it? That is also we have defined earlier. So heat transfer coefficient for the bare pipe, that is also defined earlier here, isn't it? H naught B. Only that we have to use and no overall heat transfer coefficient is required. Remember, in this case, see why overall heat transfer coefficient is required when I am having the insulated pipe, because though this inside resistance we have neglected, but there will be a resistance in this insulation and there will be resistance for outside here, outside the insulation, correct? But when we are not having this insulation, in that case only the outside heat transfer coefficient will be there in terms of H naught B. So that means whenever I am having the insulated pipe, I need to use capital U, whereas for a bare pipe, I only need to use H naught B. Do you all agree? That is what I said in the last class. Hello? Is it clear or not clear? Hello?
Sir, in the expression below, there would be an ln also, right?
Where?
ln R naught by Ri, the expression below in which you wrote the U naught.
So that I have written. No, I have not written. Just a minute. ln R naught by Ri, correct. So is it correct? So are you all able to follow what I'm saying?
Yes, sir.
Okay, so now we can calculate this for a insulated pipe. We can calculate 1 by u naught as 1. Okay, sorry. 1 by u naught will be given by 1 upon h naught is just 5, isn't it? Plus r naught is what? Outside radius, isn't it? So that will be 0.15 ln 0.15 divided by 0.05 divided by Kc, and Kc that is 0.93. So u naught we can calculate directly as u naught comes out to be, anybody? Hello? What is the value of u naught? Are you anybody is calculating?
So 0.377. So 1 upon u naught is coming 0.377.
So what is the value of u naught?
$2.65.
For bare pipe, we will have just h naught b, and that is h naught b is given as 20, isn't it? So that will be as it is. Now what will be heat loss from the insulated pipe? Heat loss from insulated pipe. Heat loss from the insulated pipe will be what? U naught A naught delta T, isn't it? U naught A naught delta T. So U naught in this case we have already obtained, that is 2.65. Area will be, heat transfer area will be what? 2 pi dl, isn't it? Correct? So 2 pi RL, what will be the area, isn't it? So 2 into 3.14 into R in this case will be what? R will be 1.5, sorry, 0.15, and assume length of pipe is 1 meter. So multiplied by just 1 into delta T will be what? Delta T will be 160 minus 30. Do you all agree?
Yes, sir.
So how much is the value? So this comes around 324.7. Is it correct? Is it correct?
Yes, sir.
And heat loss from bare pipe. Heat loss from bare pipe will be written by what? H naught B A bare and delta T. Correct. So H naught B is what? 20. What will be the area for the bare pipe? Outside heat transfer area 2 pi RL. What will be R in this case? Ri. Ri will be what? 2 into 3.14, and Ri will be 0.05 into L is just 1 into delta T will be what? 160 minus 30. Do you all agree? Is it clear or not clear?
So clear.
So what will be the value? around 816.8 watt. Do you all agree? So now this first factor is what? This first factor is the heat loss from the bare pipe. Sorry, heat loss from the insulated pipe, and this is heat loss from the bare pipe. So what does these two factors are giving me the information? These two factors is kind of providing me the information that if I use the insulation, how much heat loss I can save. Do you all agree? Yes or no? So saving in heat loss will be what? Saving in the heat loss will be what? 816.8 minus 324.7, right? Yes or no? So how much is the value? So this much will be 492 watt. Almost this much will be the saving. Correct?
Yes, sir.
Now this is what is what? What is the unit of watt? Joule per second. So this is the saving you are getting per second, isn't it? This is the energy saving you are getting per second. But very often what we look at it? We look at it the year wise, isn't it? Correct. So what will be the saving in yearly basis? Saving in yearly basis, saving in RS yearly basis. So how much money we can save yearly basis, that we wanted to calculate. Now this is this 492 we have obtained per second. Now that we have to convert first on a yearly basis. So 492 into 3600. So that will be the number of seconds present in per hour multiplied by 24 hour multiplied by 300 working days. So this much, what this much, energy saving you will be having over the year. Correct? Isn't it? So if this much energy saving is there, that means, and here now the steam cost is already given. So if I don't use the insulation, then what will happen? This much energy is going to get wasted by the condensation of the steam. Do you agree?
Yes, sir.
Isn't it? And the cost of the steam is already given. So I can calculate that. So multiplied by 7. What is the cost is given? If I am not wrong, what is the cost? Cost of the steam 750 rupees, isn't it? 750 rupees per ton. So 750 rupees per ton. So per kg I can calculate by dividing 1000. 1 ton is 1000, isn't it? Correct. So this much will be the amount of steam. Okay, so this is kg, rupees per kg, isn't it? And I also need to divide this by a latent heat of the steam. Then and then only I will get in the rupees, isn't it? So latent heat of the steam is given as how much? 1825 kilojoule per kg is given, isn't it? So that can be multiplied by 1000. So that is joule per kg. So this entire thing will have unit of joule per year, isn't it? This entire thing will have a unit of RS per kg, and this bracket will have a unit of what? Joule per kg, isn't it? So you can obtain the entire thing in rupees per year. So you will get this as RS per year. Do you all agree? Yes or no? Does it make sense? Whatever the manipulation we have done here. Hello? Hello?
Yes, sir.
How many of you are clear with this? Only few people?
Why do we divide with this latent heat of?
So ultimately what we are interested in? We are interested in finding the saving in rupees per yearly basis, isn't it? So this is the amount of heat loss which we are going to save per second. So heat loss we have first calculated yearly basis. So this is the heat loss on a yearly basis. Now this heat loss will be, represented in terms of what? It will be actually what will happen in the pipe. If I don't eliminate this heat loss, then what will happen? This much amount of energy is going to get wasted by the condensation of the steam. Do you all agree?
Yes, sir.
So if condensation of the steam is this much is going to happen. Now I wanted to find out. So if I am, kind of 1 kg of the steam is going to get condensed, then how much rupees that is going to cost me? That I can directly obtain 750 divided by 1000, isn't it? Now the cost of the steam is given 750 rupees per per ton is given, isn't it? So 750 by 1000, so that will give me rupees per kg. If I divide this rupees per kg by joule per kg, what I'm going to get? Rupees per joule, isn't it? If I divide this 750 by 1000 by this particular factor, latent heat of steam, then I'm going to get in what? Rupees per joule. And rupees per joule I can multiply to joule per year, I will get rupees per year. Do you agree?
Yes, sir. Yes, sir.
So that's what manipulation. This is this unit of this first bracket is joule per year. The unit of this second bracket is rupees per kg, and the unit of this denominator is joule per kg. So ultimately, by doing this analysis, what we are going to get is rupees per year. Do you agree, everyone? Hello?
Yes, sir.
So that means we are going to save how much? If I do mathematically, if I calculate the values here, what we are going to get? The values comes out to be rupees 5240 per year, isn't it? This is what we are going to get. Now let's calculate the cost of the insulation. This is the saving I am going to have per year because of the insulation which I have added. Now volume of the insulation is what? In this case, volume of the insulation will be what? Volume of insulation is 0.15 square minus 0.05 square into length, isn't it? Into length. So length is just 1. So this comes out to be 0.0628 meter cube. This is the volume. Cost of the insulation is this volume of the insulation multiplied by the cost factor. So that is 0.0628 into 15,000. So this comes around rupees 942.5. So this is the cost of the insulation. Do you all agree? Isn't it? Is it clear to everyone? This is the saving. Now the question is, how much time I will be required to pay back this cost of the insulation? Cost of the insulation is 942.5, but the saving is 5,240 per year, isn't it? So see, if this cost would have been higher than 5,240, then we would have calculated everything in terms of the compound interest which is given, isn't it? So annual interest rate is given, but in this case that annual interest rate is not at all useful to me because now This is 942 is the cost and saving is 5240. So if I divide 942 by 5240, probably I will get 1 or 2 months, isn't it? Do you all agree? So even if I apply the interest rate, maximum what, 1 day here or there will be the change. Do you agree? Yes or no?
Yes, sir.
So that means I don't need to do anything. I can just directly calculate the payback period here without considering the compound interest rate. But you need to include that compound interest rate when the payback period is more than a year, isn't it? If it is more than a year, definitely you need to divide this part, you need to divide by compound interest rate, isn't it? Remember, that is what we have seen in the last class. Optimal economic insulation thickness, isn't it? Can you remember that?
Yes, sir.
So that compound interest rate comes into the picture when we are looking at the annual basis. But here, since this cost is much lower, even if you don't use it, doesn't matter, you are going to get nearly the same answer. So payback period in this case will be 942.5 divided by 5240. So this comes around, how much is the value? So this comes around 0.1798 years. Okay, so in the month, I can multiply this by 12. We will get 2.15 months. So between 2.15 months, even this 15 we can convert into days, 0.15 into 30, let's say. So 4.5.
So this 5240 we get in a year, so we should divide by, means 5240 upon 12, because if we want to calculate the income of per month.
So that's what I have done it in the later part, Achintya. First I have calculated in years.
Okay.
Then I have multiplied here by 12. So I got in 2.15 months. So this is basically 2.2 months, 4 days, 12 hours. This is what the answer you are going to get. Do you all agree with me? But note that I have not used the compound interest rate here. If I use the compound interest rate, instead of 2 months, 4 days, I might get 2 months, 7 days or 8 days. That's it. All right. Do you all agree?
Yes, sir.
Okay. So this is the answer for the problem 1. Now let's look at the second problem. Let me just scroll a little bit up. Let me copy the problem statements.
So this answer 2 months, 4 days and 12 hours is that time is if we consider that he is getting money and directly he is transferring it to the owner, the one who wants money.
No. What we are saying is, if you purchase a insulation today, if you purchase the insulation today and apply on the pipe, then within 2 months, 4 days, the money of this insulation, this money which you have spent on this insulation is going to get repaid back in terms of saving in the transfer. Okay.
Yes, sir. So if there is no time gap in between, like if a person has to go from here and there, if there is no time gap, then
it's not about the person. Once you have applied the insulation on a pipe, the steam is going to continuously flow through the pipe, isn't it? There's nothing about the person.
No, sir. The cost, like you are saying, the cost that he has to pay back, the period
No, not he. What we are saying is whatever the saving we are going to have because of, saving in the heat loss, that saving in the heat loss is going to repay back the cost of the insulation in 2 months, 4 days. That's what we are saying.
Okay, sir. Okay, sir.
Is it clear to everyone? Hello?
Yes, sir.
Okay, so let's look at the second problem. Now, second problem is what is been given is okay. So this is based on the things which we are going to do in the next class, but maybe I'll give you a brief background about this and we will try to solve the problem also. So let's say we are having a plate. We are having a plate. This plate is at a temperature of 70 degrees Celsius. 70 degrees Celsius. This plate is maintained at a 70 degrees Celsius. Okay. And then there is a flow of the fluid is there over the plate here, only at the top surface here. So typically your boundary so boundary value problem will be represented like this, isn't it? So you are in this case you will see that the velocity of the fluid exactly at the surface here will be 0, but as you move in a y direction here, you can see that it is eventually reach to the free stream velocity. So this is the free stream velocity. Again, up to this it is mostly this boundary layer is laminar, but beyond this you start a turbulent region, isn't it? So turbulent. Beyond this, the flow is going to be turbulent. So what is been given in this particular problem is in a laminar boundary layer. This Nusselt number is given as 0.332, Reynolds number raised to the power 0.5, and Prandtl number raised to the power 0.3333. This is laminar. For turbulent, what is been given is Nusselt number is given as, these are the two equations I am writing, but here these exponents are messed it up when I have copied it from the tutorial sheet. So that is given as 0.0296, Reynolds number raised to the power 0.8, and Prandtl number raised to the power 0.333. So these equations we are going to look at in the next chapter, in the next class. Okay. But still we will solve this problem because there is nothing complicated in this problem. So just bear with me. So now what is been asked in this problem? In this problem is asked that there is a hot plate like this, and over this hot plate the fluid is flowing. The temperature of this hot plate is maintained at 70 degrees Celsius, and the temperature of the water, bulk temperature of the water is 25 degrees Celsius, and this is flowing with the velocity, free stream velocity of 1.5 meter per second. The length of the plate is 1 meter long. This length, total length is 1 meter long. This is 1 meter long. Now what happens is when a plate is subjected to a flow like this, you will see that the initial part of the boundary layer is always laminar, but as the distance from this leading edge increases, eventually my boundary layer becomes turbulent, isn't it? So typically the critical Reynolds number in this case is critical Reynolds number is 5 into 10 raised to the power 5. 5 into 10 raised to the power 5, and that is calculated as LV rho by mu. Okay. So this is the critical Reynolds number. What is critical Reynolds number? So you can see that when the Reynolds number of the fluid is increases beyond 5 into 10 raised to the power 5, then the flow is turbulent. Below this, the flow is laminar. Now, what is been given is Nusselt number is given. So Nusselt number is defined as HL by K, HL by K. That is how the Nusselt number is defined. Okay, so Nusselt number is basically used to calculate these are the correlations given in terms of Nusselt number. So you can use this correlation to back calculate the heat transfer coefficient. So you can calculate the heat transfer coefficient for a laminar region. You can calculate the heat transfer coefficient for a turbulent region, or we don't know whether this laminar region is going to be there only for a part of this length, or it will be throughout this complete length, that we don't know. So we need to calculate the Reynolds number first, and then we have to decide whether there will be both these regimes are present or only one regime is present. Okay, that is the another question here. And once we decide that whether the one regime, whether the flow is laminar or both laminar and turbulent flow is there, depending on that, we will be using both these equation. We will be calculating the heat transfer coefficient for the individual region, and then we are going to calculate the heat transfer coefficient for this entire system, which includes both laminar and turbulent. And that particular heat transfer coefficient is called as the average heat transfer coefficient. Okay, so these are the two questions which are being asked here. Calculate, determine the local and average heat transfer coefficient. Also, we have to calculate the heat supply necessary to maintain the plate at 70 degrees Celsius. So remember, the fluid is flowing across this plate, so that means it is going to take some heat along with it, isn't it? So that means if I need to maintain this plate at 70 degrees Celsius, I need to provide the heat continuously to this plate, because there is a continuous dissipation is taking place from the tube. Is the problem clear to everyone? Hello? Is the problem clear to everyone?
Yes, sir.
Sir, how did we find this critical Reynolds number? I mean, it's from the book.
Okay, so see, remember, these are the correlation. These are given from the experimental data. Remember, when we are having a pi flow, we say that the laminar flow is when the Reynolds number is less than 2100, isn't it? That's what you might have studied in fluid mechanics or transport phenomena. Yes or no?
Yes, sir.
Yes.
So similarly, there are the correlations given based on the data. Remember what? Okay, so why the concept of heat transfer coefficient came into the place? That is because we don't wanted to calculate the effect of thermal conductivity, viscosity, velocity change in the system when there is a flow of the fluid is occurring. Instead of doing that, we will calculate the heat transfer coefficient based on the data. Some empirical correlation we are going to use, and we are going to calculate the heat transfer coefficient, and that we are directly going to use in the Newton's law of cooling to calculate the heat transfer, instead of solving the entire system from the first principle. That's what we have said when we have started looking at heat transfer coefficient, isn't it? Concept of heat transfer coefficient. Do you all agree?
Yes, sir.
And
Yes.
Around the same time, I said that this heat transfer coefficient we calculate based on the empirical correlation. It's not we are calculating it from the first principle. No, we are calculating these from data, isn't it? So this correlation Nusselt number, which is given in this case, these two correlations are given, isn't it, for laminar and turbulent. So these are the empirical correlations given. Do you agree? Hello, is it clear to everyone? So more details on this we are going to see in the next class. Okay. But since this is the part of this tutorial, and usually this tutorial comes after we complete the forced convection, generally this part is known. But since this part is not known to you, I am giving a more broader perspective and more broader description here. Is it clear to everyone?
Yes, sir.
Okay. So now let's calculate. So I am saying there is a problem because we don't know whether we will have both these laminar and turbulent regimes present, or only the laminar regime is going to be present, isn't it? That depends on at what L I am going to get this critical Reynolds number. Do you agree? Yes or no? At what Reynolds number I am going to get, at what Reynolds number I am going to, at what length I am going to get this critical Reynolds number, that I don't know. If it is below 1 meter, then both the regimes are going to be present. But if this length is greater than 1 meter, in that case I will have only a laminar region. Do you all agree?
Yes, sir.
Yes, sir.
So now let's calculate this, length at which critical length LC. Calculate the critical length LC at which I get this Reynolds number equals to 5 into 10 raised to the power 5, because I need to know up to how much length my laminar region is going to be there, and up to how much length my turbulent regime is going to be there, or whether only the laminar regime is going to be there throughout this length. That I need to find out, and that I can find out only by finding this critical length. Now, in order to find out this critical length, I need to know L, V, rho and mu. Sorry, V, rho and mu. So these properties I need to know. So whenever we are looking at the forced convection, remember this is the forced convection, because the fluid is flowing with some velocity over this hot plate. So this is the example of a forced convection. So in a forced convection like this, remember at this surface, at this plate surface, the temperature will be 70 degrees Celsius, and the temperature here exactly at the boundary of this free stream velocity will be what? 25 degrees Celsius. Do you agree? Yes or no? So here the temperature will be 70 degrees Celsius. Here it is 70 degrees Celsius, and somewhere here or here the temperature will be what? Temperature will be 25 degrees Celsius. That is what is given in the problem. Yes or no? Do you all agree or not? Hello? What happened? Nobody is interested. Hello?
25 degrees Celsius will be in the bulk or at the top?
No. 75 degrees Celsius temperature will be only at the plate surface, because plate is maintained at 75 degrees Celsius. 70 degrees Celsius, sorry. Whereas bulk temperature will always be, bulk temperature along the free stream velocity, your temperature will be just 25. But between the free stream velocity and that surface of the plate, there will be a variation in the temperature from 70 to 25. Do you agree?
So is
Okay.
it like
maybe I will draw one more thing so that you will appreciate what I'm trying to say. Okay, just wait. So let's say if I draw a temperature profile, my temperature profile will look like this. So this will be 25 and this will be 70. Do you agree? This is the difference I am showing here. Do you agree?
Yes, sir.
In terms of temperature, I am saying. Yes or no? So my
yes,
temperature
sir.
here from 25, it is going to increase to 35, 45, 55, 65, all the way to 70 as I reach to this here. Yes or no?
So are we making assumption that this height is somewhere in the turbulent region, or it can be in the laminar as well? The 25
No. We have not gone to that place so far. We have not gone to that. What so see, whether I look at here and here, or whether I look at here or here, you will see that between these 2 points, my temperature is going to vary between 25 to 70. Do you all agree or not? Here also it will be 25 and here it will be 70. So between these 2 points, there will be distribution of the temperature. Same is going to be there here and here. I am saying the temperature will be between 25 and 70 between these 2 points along the same, vertical plane. Yes or no?
Yes, sir.
Yes, sir.
So that means what I'm trying to say is I need to find out LV, rho and mu. Sorry, V, rho and mu. These are the properties of the fluid here. and properties of the fluid depends on the temperature. So which temperature I should take? That is the question. Can you see the point? Which temperature I should take now? Did you see the problem? Why I'm, trying to give a perspective in more detail here. I am saying the temperature here will be 25. Here at the surface it is going to be 75. And I need to calculate Reynolds number for the fluid which is flowing between. So which density and which viscosity I should take, because density and viscosity will be dependent on temperature. So which one I should take? So for this, first we have to calculate the average temperature. So average temperature in this case will be what? 25.
So we have to integrate by integrating.
So that is going to make a lot of complications, because then you require a velocity profile and other things, isn't it? So simple way, and this is what usually done in forced convection. In a forced convection, whenever we are looking at such systems where the surface temperature is different and bulk temperature is different, then what you do is you take the average between the surface temperature and bulk temperature. So surface temperature here is 70, bulk temperature is 25. You take the average of that. So that comes out to be 47.5, and you calculate the properties. Calculate the properties at average temperature. Average temperature. Now in this case, once we have obtained this average temperature, now what you can do is you can go back and see the backside tables of the book, and you can find out the properties of water. Remember, in this case, water has been given. So property of water and air is already given backside of the book in the tables. So you can look at those tables and you can find out the properties. So at this average temperature, the properties given are, at the average temperature, the properties of water are given. At the average temperature, of water are given as, so properties of water is given as rho comes out to be 989. If you look at the table, this is what you are going to get: kg per meter cube. Viscosity is 5.77 into 10 raised to power minus 4 kg per meter second. Specific heat is 4180 joule per kg per degree Celsius. Thermal conductivity comes out to be 0.64 watt per meter degree Celsius, and Prandtl number is given as 3.77. So these properties you have obtained from the table given backside of the book, backside of BK Datta. Is it clear? Is it clear to everyone? Now let's calculate LC. Now you can calculate LC, isn't it? So LC will be what? 5 into 10 raised to the power 5 into mu divided by V rho, isn't it? So 5 into 10 raised to power 5. What is the value of mu here? Mu we have already given 5.77 into 10 raised to power minus 4 divided by velocity is already given. What is the free stream velocity given? Anyone? 1.5, isn't it? In the problem statement, what is the velocity given?
1.5.
1.5 meter per second, correct. And what is the density? Density also 989. So what we get is LC comes out to be 0.94 0.1945 meter. Yes or no? Is it clear to everyone?
Yes, sir.
So from this, what we can conclude now? What we can conclude? We can conclude that both laminar and turbulent region are going to be present, because up to 0 to LC I will have a laminar region, and from LC to 1 meter I am going to have a turbulent region. Remember, isn't it? That's what we have seen here. The total length is 1 meter. Now I am saying that my laminar region is going to be 0 to 0.1945 meter. So in between somewhere here. Do you all agree? Yes or no?
Yes, sir.
So this length here will be, up to this will be 0.1945 meter, and beyond this will be the turbulent region. All right. So now once we have obtained this critical length here, now I can put that value in this and calculate. Now I can, based on that, I can calculate the local and the average heat transfer coefficient, isn't it? So let's look at both these regions one by one. Okay, so now for laminar region, what will be the Nusselt number? Let's say Hx by K, and that is given as 0.332. What is the Reynolds number? Xv rho by mu raised to the power 1 by 2, and Prandtl number raised to the power 1 by 8, and this is valid. So if you put all the values here, if you put all the values here, 0.332 x raised to the power 1 by 2, V rho is what? 1.5 into rho is value of rho is 9.989 divided by mu is 5.77 into 10 raised to power -4, and this is 1 by 2, and Prandtl number is 3.77 raised to the power Prandtl number raised to the power 1 by 3, isn't it? 1 by 3. So what we get? So this is valid for 0. This is valid for 0.1945. Do you all agree? Do you all agree? Yes or no? Hello? So this is the first correlation I have written, isn't it? 0.332 Reynolds number raised to the power 1 by 2, Prandtl number raised to the power 1 by 3. This is 1 by 3, sorry. So this comes out to be 828.2 x raised to the power 1 by 2, and this will be h dash x divided by k. So thermal conductivity also we have obtained 0.64. So from this we get h dash comes out to be Is it clear to everyone what we are doing?
Yes, sir.
So this is the local heat transfer coefficient. Local heat transfer coefficient. This is local heat transfer coefficient for laminar region. Okay. And similarly, we can find out for a turbulent region. So for a turbulent region, again, we can write down between 0.1945 x in this region, again, we can write down the expression as h double dash, let's say. So h double dash x 0.64 will be what? The another expression will be there. So another expression is given as, if I go back, the another expression is 0.0929, isn't it? So that I can write down again. So 0.02, sorry, 0.0296. 0.0296 Reynolds number in this case will be what again? X V rho X V rho so let's put it in the original. So this will be the X V rho by mu raised to the power 4/5. Sorry. Prandtl number raised to the power 1/3. So again, we can put all the values here. So we will have h double dash x divided by 0.64 as it is 0.0296 x into V is 1.5, rho is 989. Rho is 989, isn't it? Rho is 989. Yes, okay. So divided by 5.77 into 10 raised to power minus 4 raised to the power 4/5. Prandtl number is 3.77 raised to the power 1/3. And if we rearrange everything, what we get is, from this what we are going to get is h double dash will be obtained as 3958 x raised to the power minus 1/5. So this is local heat transfer coefficient for turbulent flow. Is it clear to everyone up to this? Hello? Is it clear?
Yes, sir.
Now, these are the local heat transfer coefficient, but the average heat transfer coefficient will be given by what? H average will be given by what? 1/L integral of h dash dx 0 to 0.1945 plus 0.1945 to 1 h double dash dx. Do you all agree?
Sir, it is a discontinuous function because you are doing separate integrals.
But both are connected in the same plate, isn't it? So I can find out the average heat transfer coefficient with respect to the complete plate, isn't it? So up to 0.1945, the first heat transfer coefficient is there. So that's why I am, averaging over the length here, isn't it? So this I have integrated with respect to dx both. And both the expressions are in terms of x. Can you see?
Yes, sir.
So now we can put, so L is just 1, so that is anyway taken care of. So what we are going to get is 0 to 1945 h So first expression is 530. 530 x raised to the power minus 1 by 3, isn't it? Sorry, 1 by 2. This is the first expression, dx plus 0.1945 to 1. The second expression is 3958 x raised to the power minus 1 by 5 dx. And both this differential you can solve. Both this integral you can solve, and after solving this, what you are going to get is this is the first integral you are going to get like this, and second 3958 into 5 by 4 4 by 5 0.1945 and 1. So if you calculate the values, what you are going to get is 4083 H average watt per meter square degree Celsius. Is it clear to everyone what we have done so far? Hello? Is it clear to everyone? Yes or no?
Yes, sir.
Okay. Now let's look at the last part. In the last part, what is being asked is how much amount of heat should be continuously supplied to the plate in order to maintain the temperature of the plate at 70 degrees Celsius. Correct. So what will be the heat loss? So heat supplied to the plate will be what? Heat loss, isn't it? Heat loss. Do you all agree or not? So whatever the heat loss to the fluid should be supplied continuously to the plate in order to maintain the plate at 70 degrees Celsius. Yes or no? So that will be H average A delta T. So H average is 4083. Area will be what? Area of the plate will be what? Area of the plate will be length into width, isn't it? So let's assume that the length and the width both are just 1 meter. So we will have 1 into delta T. So delta T will be what?
75 minus 20.
70 minus 25. So what we are going to get is 18.37. So maybe even if we get rid of this part, this will be given as watt per meter square. Do you all agree? Sorry, into 10 raised to power 3. Hello? Is it clear to everyone? Hello? Is it clear to everyone?
Sir, I have a small doubt. Why we have integrated, like we have put the x value from laminar flow it is 0.1945, and for the turbulent flow it is
So
8.
usually, okay, I give you why we calculated H average. So typically in such cases, the average heat transfer coefficient is reported instead of reporting the local heat transfer coefficient. Remember, in this case, if you look at, okay, maybe I'll just go back to the system. So here you can see your heat transfer coefficient is going to vary across this length. Whatever you are having here may not remain the same, just, you know, after some distance here. Okay, even in the laminar region, I'm saying. So you calculate the heat transfer coefficient averaged over the entire length. Is it clear? So see here exactly. Okay, maybe I'll just. So your heat transfer coefficient here and here will not be same. because your velocity profile is changing here. You can see. So your heat transfer coefficient both are going to be different. Remember, heat transfer coefficient also depends on the velocity. Yes or no?
Yes, sir, I got.
And the velocity is changing as you are moving from this leading edge. So very often, instead of representing the heat transfer coefficient in terms of x, that will be the local heat transfer coefficient, isn't it? I am interested in what will be the average heat transfer coefficient for this entire plate. So typically, heat transfer coefficient is represented as an average heat transfer coefficient instead of reporting it as a local heat transfer coefficient, because local heat transfer coefficient can change at the locations, different locations. Do you all agree? Yes or no?
Yes, sir. Yes, sir. Thank you, sir.
Okay. So is there any question?
Sir, I wanted to ask one question that the minor exam would be proctored.
Yes.
Sir, in my area there are frequent electric cuts. So anytime the camera can go off. So like.
Okay. So if the camera goes off, then you will be considered as absent.
But sir, there are frequent electric cuts. So
1 hour, yeah. This examination is going to be there only for a 1 hour. I am not able to see that it is every 10 minutes there is no power off, I guess, isn't it? And anyway, your computer will have some battery backup, isn't it?
Yes, sir, but.
So 1 hour battery backup everybody has in the computer, and if you do not have, arrange it, whatever you wanted to do. But if the camera goes off, it will be considered as a absent. And since we are doing 3 quizzes, you have a choice of missing one, but there will not be any re-quiz. There will not be any re-quiz, re-minor, nothing doing. Only 3. So that additional third is only for this. So that because of some emergency or because of some problem, if you have missed, you will have one more chance to give. That's why the 3 is there. And that's why we are keeping best 2 out of 3. But there will not be any re-quiz, there will not be any re-minor, nothing doing. Only 2. 2 will be compulsory, and 1 you have a choice of missing by because of some failure or because of your own will. No problem in that, but we will stick to our policy. Okay.
Sir, like if a camera goes out for 10 minutes, then would it be considered or?
Then it will be considered as absent. If your camera even goes for a 5 minutes off, we will be considering you as absent. Is it clear? Yes, no. Achinta, I am sorry to be saying like this, but I have seen people misusing the liberty given. I don't mind, and I don't want it to proctor you like this, any one of you, but that's how things are happening, because nobody is following the model code of conduct, and because of that we have to do this. And I myself is helpless in this. I particularly don't want it to monitor the students like this, and but what our previous experience is, we see that this is the only way to maintain the integrity of the examinations. Okay. So I am apologizing if you are facing some problem because of this, but in the in the interest of the whole batch, I feel this is the good thing to do. All right, guys, let us stop here. Unless you have any question. I'm sorry for extending today a little bit more.